Welcome back. Here I am, just going over Chapter 2 with you all today. So Chapter 2 is our Introduction to Descriptive Statistics. A lot of what you're going to see in Chapter 2, you would have already seen, whether it be in an Algebra 1 or an Algebra 2 course. But we're going to do a review of it, just kind of a deep dive. To make sure that you understand these basics. These basics we're going to refer back to over and over and over again throughout this course. So I would say that this is probably one of the most important foundational chapters for you to understand. So make sure you take your time and you very carefully review, practice, these problems. One of the things I want to mention to you is that yes, this is also the first chapter that you will be quizzed on, and that quiz is in my courses. But I'm not posting additional homework assignments for you to do, but that is something that I strongly recommend that you do on your own. And the reason I recommend that is because, yeah, there might be some example problems that I'll be going over in these instructional videos, but unless you're able to actually practice them, and prove to yourself that you truly understand it, that's the only way that you're going to make sure that you understand these particular problems and that you're actually prepared for the quizzes when you take them. Okay, so first, learning objectives: to learn to interpret the meaning of three graphical representations of sets of data. Stem, leaf diagrams, frequency histograms, relative frequency histograms, to learn the concept of the center of a data set. To learn the concept, to learn the meaning of each of the three measures of center of a data set, the mean, the median, and the mode. That's something that should be very, very familiar to all of you at this point. To learn the concept of the variability of a data set, which would get us into the variance, the standard deviation, which is kind of our next data point here in the range. And then also, learning objectives: to learn the concept of relative position of an element of a data set, so where a particular data point might fall across the entire range or spectrum of data. To learn the meaning of two measures, the percentile rank and the z-score. So the percentile rank and the z-score is something that we are going to refer to over and over and over again in this class. So if I can ask you to highlight anything, it would be z-score. Know the z-score, understand the z-score. When we get to that section, make sure you're stressing the importance of how you calculate a z-score. To learn the meaning of three quartiles associated to a data set and how to compute them. That is typically with a box plot, or how, like I refer to, or how I was taught it, a box and whisker plot. But the first thing we're going to do is we're going to take a look at a stem and leaf diagram and how it can transform into a histogram. So basically, a stem and leaf diagram is basically just a frequency table. That's all it is. So, or actually, no, I'm sorry. It is not a frequency table. A stem and leaf diagram basically works in this way. So we have 2 and 5. Actually, I'm sorry, it is a frequency table. It can be looked at in a couple of different ways. So we have our stem and leaf plot, which is a frequency table, but it also helps us to organize data in a number of different ways. So this table right here represents a collection of data, and right now I'm actually going to list all of that data for you. All right. The 2, 3, 4, 5, 6, 7, 8, 9, and 10, I would say the 2 through 9 really represent the tens digit, where these values represent the ones digit. So this would represent the number 25. This would represent the number 3 and nothing, not 0. So there's actually no values that represent 30 in this data set. This would represent the value 40, 4, 0, the tens digit, the ones digit, 58, 69, 68, 69, 77, 73, 76, 70, 73, 73, 70, 71, 78, 74, and so on. Okay, and this would obviously be 100 and 100. I'm not going to go over the 8 and the 9 because it works the same way as these guys do. But it works out like a histogram as well, because if you were to flip it, you can see that we have the most values that are in the 70s, right? How high it is. If we turned it from here to here, you would see that this is the largest, and it would be kind of a histogram type plot. All right, so let's take a look. So the numbers in the 10 spaces, 2 through 9, this is actually what I explained already. The number in the units place is the leaf. So we have the stem, which is in the tens place, and we have the units place, which is the leaf. Okay. And then now this is what we call an organized stem and leaf plot. And all they did was they took this one and they put it in order. So notice here we'll look at 7 in particular. It goes 0, 0, 1, 3, 3, 3, 4, 6, 7, 8. So all we're doing is putting those values in order. So we can now, if we wanted to, write these numbers from least to greatest. Observations are grouped into several classes and the frequencies of each class. These classes are arranged and indicated in order on the horizontal axis. Okay, so this is the frequency histogram. So basically this is what I was talking about. All we did was take this and flip it on its side and we get the histogram. And notice, like we had pointed at earlier, 70 has the most values here. Okay, now what this represents is the frequency. So if you go across, this would look as if we have 10 values that are in the 70 range. All right, and then we could go here and we could count them if we wanted to, just to be sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we do actually have 10 values, and that's how that is represented. Okay, here would be 1 value, no values, 1 value, 1 value. This would probably be 3 because it's in between the 4 and the 2, and so on. Relative frequency histograms. So they are exactly the same as frequency histograms, except that the vertical axis in the relative frequency histogram is not frequency, but relative frequency. Classes are selected. The relative frequency of each class is noted. The classes are arranged and indicated in order on the horizontal axis. For each class, a vertical bar whose length is the relative frequency of the class is drawn. The resulting display is a relative frequency histogram for the data. Okay, so if we take a look at this sample size and relative frequency histogram. So this is a small sample size, this is a medium sample size, this is a large sample size, and notice when you have a large sample size, it's actually forming a shape of some sort. This is what we would call a bell curve, a standard normal bell curve, all right? But notice it's a very large sample. You can't even see the bars anymore because there's so many of them, and it just turns into this smooth, nice little curve here. Okay. So a very fine relative frequency histogram, okay, would represent this shaded portion of data, portion between A and B. Okay, now we're going to talk about the mean. So the sample mean of a set of n sample data is represented as X with a bar over it. Okay, that's like an italicized X with a bar over it. We say sample mean because we're only grabbing a sample of the data. So if we were, say we're talking about the United States and we are surveying everybody in the United States, that would not be a sample, that would be the entire population. But if we're just grabbing a small sample from there, maybe I sent out a random survey to random people in the United States, and maybe I only sent out 50 surveys to 50 random people, that would be the sample. And then the mean, or the average of that sample, would be the sample mean. To calculate it, right, all you do is you add up all of your values that you get from the sample, or your scores, or your temperatures, or whatever they might be that you're measuring, and then you divide it by the sample size, which is n. Okay? The population mean of a set of the population is the number, and this looks like a U here, but it's actually the Greek symbol mu. We spell that M-U, okay? But that would represent the entire population, and N doesn't represent The sample size, N, represents the entire population of people. So we have two different ways of writing the mean. We have our sample mean, which is just a smaller collection, and then we have our population mean, which is everybody in the entire collection. Okay? These two concepts are important because we're going to be toggling back and forth between the sample mean, or the sample, and then the population mean, or the entire population. Knowing the difference between those two is going to be very, very helpful. So the median. Now in the median, we also have a sample median. All right, the median happens to be the middle number. Once we arrange all of our values in numerical order from least to greatest. Okay, the mean, if you count in from the outside and you go right to the middle, that represents your mean. Okay, the sample median of a set of data for which there are even numbers of measurements is the mean of the two middle measurements. So that's an important piece too. So let's say we had 10 values. Okay, if we had 10 values, we couldn't find the exact middle value. We would have to take the average of the two middle values. So basically we would end up taking the average of the fifth value and the sixth value. All right, so the fifth value and the sixth value. We would take the average of those, and that would give us our median right there. Example, compute the sample median for the data 0, -1, 2, and 2. Okay, so the solution, the data in numerical order, we need to put them in order, and then we need to go ahead, so negative is all the way to the left, 0, 2, 2, and then we find the exact middle. The middle is right here, in between 0 and 2, so you take the average of them. 0 plus 2 divided by 2 would give you 1, so the median of that data would be 1. And then the mode would be the most frequent value. So in this particular data set, we have 0 shows up twice, so therefore 0 is the mode. The range is the largest value in the data set minus the smallest value. Okay, that's all the range is, the largest value minus the smallest value. Now, this is where things start to get a little bit more complicated. So we need to calculate the variance, and there is a formula here that you need to remember, you need to memorize, you need to write down. The variance formula, okay, in variance is denoted by the value s squared. That's what variance means. We use s squared to denote the variance. What you do is you take every data value and you subtract from it the sample mean, okay? And then once you subtract the sample mean from every data value, you then add them all together. I'm sorry, before you add them together, you square it, then you add them all together and then divide it by the sample number of individuals, so the number of sample data minus 1, okay? That's how you calculate it. The algebraic equivalent, all right, to this formula would be this one right here. We're going to use this, and I'll probably do an example problem when we meet just to kind of go over this a little bit further. And then the standard deviation is basically the same as the variance, but the only thing you do is take the square root of this. So if you took the square root of both sides of this equation or this one, you would end up getting, what's the square root of s squared? It's just simply s. That's it. So and s represents the standard deviation. So in this case right here, this would be the formula for the standard deviation, okay? So the population variance. So one thing I want to separate between is I want to separate between this Greek symbol here, which actually is called sigma, S-I-G-M-A. That represents the population variance. Sigma squared is the population variance, and S squared is the sample variance, where sigma is the population standard deviation and S is the sample standard deviation. So again, being able to go back and forth between the sample and the population, hugely valuable in understanding that. So I'm actually going to end my video right here.